There are a few different ways that we can list the electron arrangements within an atom. As we previously saw, we can write out the 4 quantum numbers to describe different electrons that are within the atom. Those quantum numbers were N, L, M sub L, and M sub S. We can also write electron configurations and orbital diagrams. Electron configurations are also called the atom's electronic structure. It's useful because an atom's electron configuration will control how that element will react and what type of chemical properties it has. Electron configurations show the distribution of electrons among the orbitals of an atom. We list the shell and the subshell and how many electrons are populating that subshell. We list the electron population by writing a superscript number with how many electrons that subshell contains. So for example, for hydrogen, hydrogen is the simplest element with only one electron, so its atomic number, or Z, is equal to 1. We would only have one electron to place. The lowest energy orbital is a 1s orbital. The 1 represents the shell, which is our N value in terms of our quantum numbers. The S represents our subshell, which is our L value in terms of quantum numbers. And the superscript value 1 tells us that there's 1 electrons inside of that 1s subshell. This configuration of 1s1 represents something called the ground state electron configuration. The ground state is the lowest energy configuration that we can write for a specific element. To arrive at the electron configurations of another element, we have to imagine that starting after hydrogen, we add 1 proton to the nucleus each time and 1 electron to orbitals outside of the nucleus. When we fill those orbitals, think about them like filling a hotel. You want to start on the lowest ground floor, which is the lowest in energy. In this case, the lowest energy orbital is going to be the 1s orbital. Each orbital is represented by a line, and we can hold 2 electrons per orbital. So then once this first 1s orbital is filled, we would then move up to the 2s orbital. The 2s orbital can hold 2 electrons. It's the next lowest in energy. And then once the 2s orbital is filled, we'll move to the 2p subshell. Now notice there's 3 lines that are drawn for the 2p subshell, 1, 2, 3. That's because there's 3 degenerate p orbitals in any p subshell. Degenerate means that they're all of equal energy. So the p subshell can hold 6 electrons, or 2 per orbital. After we fill up the p subshell, we would move to the 3s subshell. In any s subshell, there's only 1 orbital, so we could hold 2 more electrons there. After 3s, we would move to the next lowest in energy, which is 3p. Just like we saw with the 2p, there's 3 equal energy 3p orbitals inside of that subshell. And then, interestingly enough, after the 3p subshell is filled, we actually fill the 4s. The 4s is a little bit lower in energy than the 3d. So after the 4s is filled with its 2 electrons, we would then start filling the 3d subshell. The 3d subshell has 5 orbitals, so we represent that with 5 lines. Each one of them can hold 2 electrons, so any d subshell can hold 10 electrons. And then we would keep continuing with this pattern for filling, starting with the lowest energy and building up our atom 1 electron at a time. This process of building up the atomic structure by adding electrons one at a time to the lowest available energy orbital is called the Aufbau principle. And Aufbau just means German for building up. So one at a time, we add 1 electron and we fill up our orbitals with 2 electrons, and then we have to move on to the next lowest energy. And we would add enough electrons to equal the atomic number of our element for a neutral atom. The diagonal rule is one way to help you remember the filling order of the subshells. This follows the energy diagram that we just saw previously. If you were to draw diagonal lines through each of these, it would tell us the order. So first we would fill the 1s, then we would fill the 2s, then the 2p and the 3s, followed by the 3p and then the 4s subshell. Then we would fill the 3d, the 4p, the 5s, then the 4d, the 5p, the 6s. After 6s, we would fill the 4f, the 5d, the 6p, the 7s. And then lastly, the 5f, the 6d, and the 7p. The other way to remember is to use the periodic table to actually tell you the filling order. You don't have to memorize anything because the order of the periodic table from left to right will tell us exactly the order that the energy levels will fill. We can read the periodic table like a book from left to right in order to determine the filling order for the energy levels. Notice that in the S block, there's 2 columns. That's because in every S subshell, there's only 1 orbital, and each column would contribute 1 electron, and we can have 2 electrons per orbital. In our P block, there's 6 columns, and each column, 2 of them would fill 1 orbital essentially. So therefore, there's going to be 3 orbitals in every P subshell. And then in our D block, there's 10 columns, and that's because there's 5 orbitals. We usually won't write configurations that very much for elements that are from the F block, but down in the F block, there are 14 columns, and that would represent 7 orbitals. So looking at our periodic table on the left, if we start in the first period here, the first 2 elements would be hydrogen and helium. Hydrogen would contribute 1 electron to half fill the 1s orbital, which is the lowest in energy. And helium would contribute that second electron, which would make our 1s orbital completely full. And so if we continue along, reading it like a book, the next step is that we're at the 2s. Second period in the S block, the elements in the alkaline metals and the alkaline earth metals would fill the 2s orbital. And then moving along to the P block, the next lowest in energy, would be those next 6 elements, ranging from boron to our noble gas neon in the second row. And those would fill all 3 of the 2p orbitals. So then our 2p subshell will be full, and then we would have to move over to the third period. The next lowest energy orbital that will fill will be the 3s, and that'll come from our group 1a, 2a. And then moving over, we would next go to the 3p. And those next 6 elements or 6 electrons that those elements contribute would fill our 3p subshell. And then after 3p, we would have to go to the fourth period. We would fill the 4s at this point, which is our trend. We actually fill 4s before we fill 3d. It's a little bit lower in energy. So after the 4s is filled with 2 electrons, we then would move through our 3d subshell. Our 3d subshell contains 5 orbitals, so these next 10 elements would fill up the 3d subshell. After 3d, we would move to 4p. The next 6 electrons that the next 6 elements contribute would fill up the 4p, and after that's full, we would move to period 5. The next lowest energy is 5s. After 2 electrons go into the 5s, we then move to the 4d. 10 electrons will fill the 4d, and we'll move to 5p. Next 6 electrons would fill 5p, and then we'd move to 6s, and so on. So we can read the periodic table, and knowing where the S block, P block, and D block are, and the F block, we can determine exactly what orbital we'll be filling at any given time, and we can see that order of building up. So we're going to practice writing some electron configurations for the first 10 elements, hydrogen through neon. And if you want to keep out that handout that has your electron orbital filling sequence in order, you can look at that. And if you also want to use your periodic table to help you determine the filling order as well. So for our first atom, we have hydrogen, and hydrogen's atomic number is 1, so Z is equal to 1. Our electron configuration is we're going to have to start with our lowest energy orbital, which is 1s, and we'll list the electron population. The Z number tells us the electron population total. There's only 1 electron to place, so we're going to put 1 electron in that 1s orbital. For helium, Z is equal to 2, and we know our 1s orbital can hold another electron, So our configuration for helium is going to be 1s2. For lithium, the atomic number is 3, so Z is equal to 3. And our 1s orbital is going to be filled, 1s2. We have 2 electrons that are still in the 1s orbital for lithium, but we have to place 3 electrons total. So we have 1 more electron to place, and that next electron is going to have to go into the lowest available orbital. Then the next lowest in energy will be the 2s. And so in that 2s orbital, there's going to be just 1 electron. If you were to add up the superscripts 2 and 1, 1 plus 2 equals 3, which that equals our Z value in each case, or our atomic number, which is equal to our number of electrons for a neutral atom. So protons is equal to the number of electrons. For beryllium, we're building up here. Z is equal to 4. Our electron configuration for the 1s orbital is going to be 1s2. The 1s is completely filled. And our next lowest in energy was the 2s orbital. And that one was half filled with lithium, but now it's going to be completely filled. We're going to say 2s2 because now we have 2 electrons occupying that 2s orbital. For boron, Z is equal to 5. So that means we have 5 electrons to place. The first 2 will go into the 1s. The next 2 will go into the 2s. But since our 2s was filled, now we have to move to the next lowest in energy that's available. And boron is over in that P block. And so the next available in energy is going to be the 2p subshell. The 2p subshell can hold a total of 6 electrons. Right now, though, we only have 1 more electron to place because we've already placed 4 of them. So we only have 1 more to put into that 2p subshell. So that would represent all 5 of our electrons for boron. 1s2, 2s2, 2p1. Continuing on, we're at carbon. The atomic number of carbon is 6, so Z is equal to 6. We're first going to put our first 2 electrons in the 1s orbital, so we'll have 1s2. The next lowest in energy is 2s, so we'll have 2s2. And then we moved last with boron to the 2p. We said the 2p can hold 6 electrons, and we have 2 more electrons that we still need to place, so we're going to have 2p2 for carbon. For nitrogen, the atomic number is equal to 7. So our electron configuration is going to be 1s2, 2s2, 2p. We have 3 in this case. And if we take 2 plus 2 plus 3, that equals 7. When we add up those superscript values, they add up to our total electron population in each case. At this point, our 2p subshell is half filled. In our 2p subshell, there's 3 equal energy 2p orbitals. So when we go to oxygen now, where the atomic number Z is equal to 8, we're going to have 1s2, 2s2, 2p4. Moving to fluorine, the atomic number is equal to 9. We would have 1s2, 2s2, 2p5. Now there's 5 electrons in our p subshell. And for neon, where the atomic number is equal to 10, that's going to be the last electron that fills our 2p subshell. So our configuration will be 1s2, 2s2, 2p6. And now our p subshell is completely filled with neon. And if you're following along with your periodic table, you would have to move over to the 3rd period now because our last electron represented the last one in that 2nd period. Orbital diagrams, or sometimes called orbital box diagrams, are another way to represent the electrons in orbitals. They give us a lot of information because they don't just tell us the configuration, but they tell us what electrons are paired up and what electrons are unpaired. We represent each orbital with either a line or a circle or a box, just something to show each orbital itself. And then we use up and down arrows to show that our electrons have opposite spins and they're paired inside of each orbital. So for example, we could write the configuration for nitrogen. And our nitrogen configuration, we had Z was equal to 7. So that was 1s2, 2s2, 2p3. So that told us that in our 1s orbital, there was a total of 2 electrons, and we would say those electrons come together with their spins paired. So we would draw inside of our 1s orbital one arrow pointing up. That represents an electron with a spin of plus 1/2. And then we would draw another electron with an arrow pointing down. That down arrow represents an electron with a spin of negative 1/2. So now our 1s orbital is filled and the electrons have their spins paired, or one is going clockwise and one is going counterclockwise. So in this example, I used circles to represent my orbitals. Then next we're filling the 2s. The 2s orbital holds 2 electrons, so we would have one pointed up, one pointed down. So now we've placed the first 4 electrons for nitrogen. And then moving over to the 2p, we draw all 3 orbitals for 2p, even if some of them are empty. And when we fill our 2p orbitals, because these are degenerate, which means equal in energy, we're going to have to decide how we end up populating those orbitals. What we'll see is going to happen is first one electron will go into one of the 2p orbitals, and then another electron will go into another empty 2p orbital, and that last third electron will fill the last empty 2p orbital first, before they actually pair up with one another. So this is something we'll talk about in a little bit called Hund's rule, but you can think about electrons as wanting to get as far away from each other as possible, and they won't pair up with their spins until they absolutely have to. For our first 10 elements that we wrote our electron configurations for, now let's draw the orbital diagrams for each of those. So for hydrogen, our configuration is 1s1. That means we would draw a line and we would write the orbital underneath it that we're filling, so 1s, and we only have one electron that we have to populate, so we would just draw one arrow pointed up. For helium, our configuration is 1s2, so we're still in that 1s orbital, but now we're going to have 2 electrons, so one pointed up, one pointed down. Their spins are paired. Our 1s orbital is filled, so when we go to lithium, we're going to have 2 orbitals that we need. We're going to have 1s and we're going to have 2s. Our 1s is filled, so our configuration is 1s2. We have 2 electrons in the 1s, and we're only going to have 1 electron inside of the 2s orbital. Beryllium, we're going to have 1s, 2s. Our 1s has 2 electrons in it, and now our 2s has 2 electrons in it. We placed all 4 electrons. 1s is full, 2s is full. So moving to boron, where the configuration is 1s2, 2s2, 2p1, now we're going to have to draw all of our p orbitals as well. So 1s, 2s, and then 1, 2, 3 2p orbitals that are all equal energy. So our 1s, we've got 2 electrons there. We've got 2 electrons in our 2s, and we've got 1 electron in our 2p subshell. So something that we saw when we were just looking at our quick example with nitrogen, drawing our orbital diagrams, was that when we had to decide where to put that next electron in those p orbitals, is that we put it into a separate orbital instead of pairing up those spins. This is something known as Hund's rule. So Hund's rule says that the most stable arrangement of the electrons in orbitals of equal energy, just like those 3p orbitals, which were degenerate orbitals, is the one in which the number of electrons has the same spin maximized, or in other words, they are all spin up and spaced out amongst the orbitals before they're paired up together. If we have more than one orbital of all same energy, so if we have 3 2p orbitals or 5 3d orbitals, first we're going to put one electron into each orbital with their spins parallel, or meaning they're all spin up. So first we would half fill all of our orbitals that are equal energy. Only after those orbitals are half filled, then will we come back and start pairing up those spins and completely filling the equal energy orbitals. And this is because electrons are negatively charged, and they're going to have repulsions with one another. And those repulsions are going to cause them to want to spread out and not occupy the same space unless they have to. So first they all half fill their own orbitals, then they come back and completely fill them because it's still lower in energy than jumping up to the next energy level. Now that we've talked about Hund's rule, let's continue drawing our orbital diagrams. So for carbon, this would be the first one where we'd have to make a decision. We have 1s2, 2s2, and then 2p2. So we've got 1, 2, 3 equal energy 2p orbitals. Our 1s orbital is filled, so spin up, spin down. Our 2s orbital is filled. And for our p subshell, we've got 2 electrons. So our first one would go here, and our second one would go into the next orbital. It would not pair up with that first one yet. For nitrogen, we've got 1s2, 2s2, 2p3. So 1s, 2s, and our 2p. We're going to have our 1s filled, our 2s orbital filled, and our p subshell now is going to have 3 electrons that we have to place. So 1, 2, 3. The spins are all parallel, so they're all using an up arrow, and the spin is maximized, or the electrons are half filling the orbitals before we go back and fill them completely. Now for oxygen, our configuration is 1s2, 2s2, 2p4. And since with nitrogen we saw that we half filled all of our 2p orbitals, now we're going to have to start completely filling some of them up. So 1s, 2s, and then here's our 3 2p orbitals. So we're going to have our 1s filled, our 2s filled, and then our first 1, 2, 3 electrons, and then we would go back to that first one and draw a down arrow to represent, hey, now that orbital is completely filled. It has 2 electrons occupying it. For fluorine, we're going to have 1s2, 2s2, 2p5. So we've got 1s, 2s, and 3 2p orbitals. So 1s has 2 electrons, 2s has 2 electrons, and then the 2p has 5. So 1, 2, 3, 4, 5. So now 2 of the 2p orbitals are completely filled, and 1 of the 2p orbitals is still half filled. So we can only fit 1 more electron in our 2p subshell before we'd have to move to the next lowest in energy. And neon is going to take up that last electron, and that's the last one in the second period of the p block. So 1s2, 2s2, 2p6. We have 1s, 2s, and then 2p. We're going to have 2 electrons in our 1s, 2 electrons in our 2s, and then 1, 2, 3, 4, 5, 6 electrons completely filling up our 2p subshell. So using lines or circles or boxes, this is a way to show the orbital diagram, and from this we can actually determine some properties of the elements based upon if all of the electron spins are paired, or if only some of them have spins that are paired and some of them are left unpaired, etc. We have seen that when electrons occupy the same orbital, they have the same first 3 quantum numbers. They have the same value of n, l, and m sub l if they're living in the exact same orbital. The only quantum number that's different is their m sub s, or their spin. When they're in the same orbital, we say that their spins are paired. And this pairing of spins cancels out the magnetic properties of a sample. So if 2 electrons are in the exact same orbital, and they have 2 different spins, we could say spin up and spin down. What's going to happen is they are going to not have any magnetic effects because their spins are paired. You can think about it like the north pole of one electron magnet is opposite the south pole of another. Therefore, their magnetic effects cancel. So when they cancel, we say that it's diamagnetic. The sample is diamagnetic. It's not attracted to a magnetic field. In fact, diamagnetic samples are actually weakly repelled by a magnet. The other situation we can have is we can have 2 electrons in different orbitals, and they would have the same spin if they're in equal energy degenerate orbitals. And if that happens, we'd have a situation where we have 1 electron that's spin up and another electron in a different orbital that's spin up. In this sample, we have unpaired electrons, and the magnetic effects do not cancel. We call this paramagnetic. Paramagnetic samples are actually attracted to a magnetic field. The greater amount of unpaired electrons in a sample, the stronger the attraction to a magnetic field there will be. Paramagnetism and diamagnetism are measurable properties that can provide experimental verification of the presence or absence of unpaired electrons in substances. We can also quantitatively measure the strength of the attraction of a paramagnetic substance towards a magnetic field and calculate the number of unpaired electrons in different atoms, molecules, or ions. The easiest way to determine if something is paramagnetic or diamagnetic would be to draw its orbital diagram and see if you have any unpaired electrons in the sample. So paramagnetic substances are going to have unpaired electrons, at least one or more unpaired electron, and they will be weakly attracted to a magnetic field. Diamagnetic substances, on the other hand, have no unpaired electrons, and they are going to be not attracted or even weakly repelled by a magnetic field. If we continue along our energy diagram, filling our orbitals one at a time, starting with the lowest energy, moving to the next highest in energy, we did the first 10 elements, and that took us through the 1s, the 2s, and then the 2p. And then after the 2p is filled, we would move to the 3s, and then we would move to the 3p. This is where things get a little bit interesting. After the 3p, you might think that you're still in the third shell that you would fill the 3d, but instead what happens is the 4s actually gets filled before the 3d. The 4s is in a higher shell, but the energy is a little bit lower, and Mother Nature always likes to fill lowest energy first. So after the 3p orbitals, we will actually put electrons into the 4s. The 4s is filled before the 3d because the electrons in a 3d orbital feel a lot of repulsion between them. There's 5 3d orbitals within that subshell. And so it can hold 10 electrons, and those electrons experience a great amount of repulsion. So even though the 4s orbital is farther away, and we know it's farther away because it has a bigger n value, so n of 4 is greater than n of 3. And if you recall, that principal quantum number tells you the size of the shell or how far away the electrons live from the nucleus. It still requires less energy to pop an electron into that 4s subshell rather than the 3d because there's not as much repulsion in that 4s. A 4s subshell can only hold 2 electrons versus the 10 electrons that can be held in our 3D subshell. So when we're doing our filling and we're following it in order, after the 3p, then we're going to fill electrons into the 4s. Only after the 4s is filled will the electrons actually go back and occupy those 5 3D orbitals. So using whatever method you like to determine the filling order of the orbitals, whether it's the periodic table or the diagonal rule or just looking at your energy diagram for now, let's write out the electron configurations for the following elements. And the first thing I like to do is look at what the atomic number of each of these elements is. So we know exactly how many electrons we have to place. So for calcium, the atomic number is 20, so we'll have 20 electrons. For scandium, we have Z of 21. Titanium, our atomic number, Z is equal to 22. And then we have manganese, Z will be equal to 25. So that atomic number tells us exactly how many superscripts we should have or how many electrons will be occupying our orbitals. So for calcium, we're writing out the full ground state electron configuration. We're going to have 1s2, 2s2, 2p6, and then our 2p is filled, so now we have to move to the third row, third period. We'll have 3s2. After the 3s, we fill the 3p. We're going to have 3p6, and then after the 3p's are filled, we have to move to the fourth row, in the fourth row is where calcium is. We're going to be in that S block, so 4s, and potassium would be 4s1, and calcium will be 4s2. So that's going to be our ground state configuration for calcium. Now for scandium, that's going to be the next electron. After the 4s is filled, the next that we fill is the 3d. So that next 21st electron is going to have to occupy the 3d subshell. So for scandium, our configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d1. Our 3D subshell can hold a max of 10 electrons because there's 5 d orbitals and each can hold 2 electrons in it. So moving on to titanium now, number 22, that means our next 22nd electron is going to go in the 3D orbital as well. So our configuration here is going to look pretty much the same until the very end. 1s2, 2s2, 2p6, 3s2, 3p6, and then we fill 4s2 and 3d2. So 2 electrons in the d subshell for titanium. And for manganese, that is the 25th electron we're going to have to place, and that's going to go into the 3d subshell as well. So we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then now if we count over in the d subshell, from scandium that's 1, titanium 2, vanadium 3, chromium 4, and manganese 5, that we're going to have 3d5. So now our d subshell is half filled with manganese. You might notice that it gets really tedious writing out these electron configurations as your atomic number gets higher and higher and higher. So there's a shorthand way that we can write the electron configuration, and it's called the noble gas core method. So for example, this full configuration for lead is very long. But how we could write the shorthand notation for lead is we would look at the noble gas that precedes it. And lead is in the 6th period, and it's in the P block. Z is number 82. So if we go back and we backtrack, the previous noble gas is xenon. So we put xenons in brackets. And then everything that represents the configuration of xenon, xenon would end with 5p6. So all of this would be our electron configuration for xenon. After that, we list everything else that we did not include by writing xenon in brackets. So these electrons are still listed after our noble gas in brackets. And that's our shorthand notation. We can always look at what the preceding noble gas is listed in brackets, and then that's like saying that's the electron configuration up to that noble gas, and then we list the electrons after. So after xenon, working our way up to lead, we would have 6s2, and then actually after 6s, we would go down to 4f's, and that would be 4f14. This is where the inner transition metals pick up. Then after that, we would have our D block that we have to go to, which would be 5D10, and then we would be in the 6P block, which is where lead is contained. It's the second one in there, so the final spot there would be 6P2. Using the shorthand electron configurations is really convenient because we can quickly write the electron configurations without relisting the really long sequence over and over again. And it allows us to see really easily the valence shell and the valence electrons. So the valence shell is the outermost shell where the electrons occupy, or the highest value of n, so the highest value for that principal quantum number. The valence electrons are the electrons that reside within that highest value of n, and we call those the outermost electrons. The valence electrons are very important when we start actually looking at chemical reactions. Because they're the farthest away from the nucleus and they're in the highest value of n, they're going to be the ones that typically react when we're forming new compounds. So if we look at some of these configurations and compare the long hand configuration, which is written on the right hand side, to the shorthand noble gas core method, we have lithium, and that would be 1s2, 2s2. So helium would be the preceding noble gas. We would write that in brackets. And then after helium, there's only one electron, and that would be 2s1. So this 2s1 is still listed. We can quickly see that 2 is the valence shell, so N equal to 2 is the highest energy level where electrons live, and there's only one valence electron in that highest shell. We can quickly see that by looking at the shorthand method. For sodium, we would have neon being the preceding noble gas, so neon brackets brackets, and then after neon to get to sodium, it would just be 3s1. So this 1s2, 2s2, 2p6, that's the configuration for neon that we're not writing. In this example, sodium, highest value of N, the valence shell is 3, and there's one electron in that highest value of N, so it has one valence electron. And since all of these are in group 1A, all of these are alkali metals, they all have one valence electron. And that's going to be something that groups our periodic table together and has different substances that have the same chemical reactivity based upon their group number because they will have the same number of valence electrons. So let's look at this last one for potassium here. Potassium's preceding noble gas, if you go backwards, would be argon. So argon brackets brackets. The electron configuration for argon is 1s2, 2s2, 2p6, 3s2, 3p6. All of that represents argon. And then moving to potassium after there, there's one electron in the 4s orbital. So one valence electron, highest value of N is 4, so that's the valence shell. So let's practice writing the shorthand electron configuration for the following. We have silicon and we have nickel. So for silicon, let's find that on the periodic table. It's atomic number 14, so Z is equal to 14. And if we look back, the noble gas that comes before silicon is neon. So we're going to write neon brackets brackets. And then everything after neon up until silicon. So after neon, we would be moving to the 3s, and that's going to be sodium and magnesium. So we'll have 3s2. And then after that, we would go to the 3p. So we're going to have 3p, and 3p1 is aluminum, and 3p2 is silicon. So we're going to have 3p2. And for nickel, our atomic number for nickel is Z equals 28, so 28 electrons to place total. But we're going to use our noble gas method. So the noble gas before nickel, if we go back, is argon. So we write argon brackets brackets. And then after argon, we come to potassium, and that's in the 4s. So for potassium and calcium, we would have 4s2. And then after the 4s is filled, we actually start filling the 3d. So we're going to have 3d, and then we count over how many electrons are in the 3d for nickel. 1, 2, 3, 4, 5, 6, 7, 8. If we count over to where nickel is. So we would have argon brackets brackets, 4s2, 3d8. So the shorthand notation is very convenient, and it's much faster than writing out the longhand notation. Usually you can always write the shorthand electron configuration unless the problem specifies you to write the longhand one. There are a few electron configurations that are not exactly as we would predict them by looking on the periodic table. And they usually happen in the transition metal elements that are in the D block. So we do have some exceptions to the rules that we have to learn. For example, if we look at chromium, copper, silver, and gold, we can see where some of these exceptions occur. So for chromium, we would expect the configuration to be argon brackets brackets, 3d4, 4s2, and it doesn't matter what order you write 3d and 4s in. We would probably write that as 4s2, 3d4, but it's the same thing. And for copper, we would expect it to be 4s2, 3d9. So let's highlight the D ones here. For silver, we would expect it to be 5s2, 4d9. And for gold, we would expect it to be 6s2, 5d9. So notice copper, silver, and gold are all in the same column. And the experimental electron configuration is not what the expected is. It's close, but it's a little bit different. It's actually, for chromium, 4s1 3d5. And for copper, it's 4s1 3d10. For silver, it's 5s1 4d10. And for gold, it's 6s1 5d10. So what's happening is an electron is being promoted from the 4s or the 5s or the 6s subshell, and it's being promoted to a d subshell. And that's because having either an exactly filled or an exactly half-filled subshell has extra stability. So by promoting one of the s electrons to the d, we're half filling the s, and we're either perfectly filling the d or we're half filling the d, as in the case of chromium. So it leads to that element being a little bit more stable, having its electrons arranged in this fashion. We can see this unexpected electron configuration a little bit easier if we draw out the orbital diagrams. And let's look at chromium and copper for just two examples. So for chromium, we could write our expected configuration, argon brackets brackets, 4s2, 3d4. And so we would have our 4s, we would have our 3d, and we have 5 orbitals. So 1, 2, 3, 4, 5 orbitals in our 3d. Our 4s is going to be full with 2 electrons, and then there's going to be 4 electrons in our 3d. So 1, 2, 3, 4. And remember, each electron occupies its own orbital first with all of their spins parallel. And what's actually happening is instead of having this orbital right here on the 3d that has nothing in it, it would rather have 5 electrons in the 3d and have the 3d being completely half filled. So one of the electrons from the 4s gets promoted to the 3d that's empty. And so our real configuration is argon brackets brackets 4s1 3d5. And so our orbital diagram will look like this instead. We're going to have 1 electron in the 4s and 1 electron in each of the 5d orbitals. And so there are a few elements within the transition metals that do this in order to maximize having either completely filled or having completely half-filled d subshells. And so for copper, we have 4s2 3d9 that would be expected because copper is the 9th element within the 4th period in the d block. And so we would think it would look like this, 4s, and then our 5 3d orbitals. We would have 4s1, 4s2, 3d1, 2, 3, 4, 5, 6, 7, 8, 9. And you can see how this situation is similar to chromium. We have 4 of the 3d orbitals that are completely filled, and then we've got this one that's half filled. It would be lower in energy for the 3d orbitals to be completely filled. So one of the electrons gets promoted to this half-filled 3d orbital, and our real configuration for copper ends up being 4s1 3d10. So we have 4s and our 5 3d orbitals. We're left with 1 electron in our 4s, and now our 3d orbitals are going to have 10 electrons in them, and so they're going to be completely filled. And this is a stabilizing thing because of that extra stability from having completely half-filled or completely filled subshells. And by promoting one from the 4s, we're still leaving the 4s half-filled, but we're stabilizing the 3d subshell. We can also write the electron configuration of ions. For ions that are made from main group elements, we can predict what those charges will be for anything that's a representative element. But when we form ions, we're either going to be taking electrons away and making cations, or we're going to be adding electrons and forming anions. Adding or removing electrons is not the same thing as when we were building up our electronic structure using the Aufbau principle, where we were following that sequence for filling of starting with the lowest energy orbitals and working our way up. Because adding an electron to a nucleus that has a certain number of protons and neutrons is not the same as adding an extra and taking one away when we're not changing the nuclear charge. And we'll talk about this a little bit at the end of the chapter when we look at periodic trends. So if we look at main group elements as a basic example to start with, for a cation, we're going to remove electrons from the highest value of n. So that valence shell is where the electrons get taken away from, regardless of the filling order that the orbitals tell us. We're looking for the highest value of n. So let's imagine we're forming a sodium ion. We know sodium is a group 1A metal. Sodium always forms a +1 charge when it becomes a cation. So if we look at our electron configuration for neutral sodium, we have 1s2, 2s2, 2p6, 3s1. And that 3s1 represents our highest value of n in this case. So n is equal to 3. That's where that electron is going to get taken away from when it's removed to form a sodium ion. So if we take away one electron from our neutral sodium atom, we're going to now have a sodium ion, and what we'll be left with is its electron configuration will be 1s2, 2s2, 2p6. That 3s1 electron got removed when it became an ion. And that electron configuration of a sodium ion would be the same as the preceding noble gas, which is neon. It has the same electron configuration as neon. So if we look at calcium, for example, calcium's electron configuration, the full configuration, is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And calcium is a group 2A metal. And we know that group 2A metals form a +2 charge always. Well, why do they always form a +2 charge? Because they have 2 valence electrons and their highest value of n. So the highest value of n here is n equals 4. So when calcium loses its valence electrons, it's going to lose its 2 4s electrons. So when calcium becomes an ion, it'll become the calcium 2+ ion, and its electron configuration will be 1s2, 2s2, 2p6, 3s2, 3p6. And this is the same as its preceding noble gas as well. And for calcium, the preceding noble gas is argon. So we say that sodium and neon are isoelectronic because they have the exact same electron configuration. We could say the same thing for sodium ion, sodium ion and neon. And we say that the calcium ion and argon would also be isoelectronic because they have the same electron configuration. And let's look at anions as well. So anions, we know, have a negative charge. And usually non-metals are going to be gaining electrons and forming anions instead of metals. They like to lose electrons. So when we form an anion, we're going to have to add electrons. And we add electrons to the highest value of n, or that valence shell. The highest value of n would represent our highest shell, or our principal quantum number. So if we imagine chlorine becoming the chloride anion, we could write the electron configuration for chlorine, and that would be 1s2, 2s2, 2p6, 3s2, 3p5, so it's a halogen. And chlorine is in group 7A, and in group 7A we know that those halogens form a -1 charge. Well, why do they form a -1 charge? Why do they only like to gain 1 electron? Because in our highest shell, which is the 3p right here, there's only 5 electrons right now. And we know that any p subshell can have a max of 6 electrons. So they're trying to become stable by filling completely that p subshell. So when chlorine gains 1 electron, it'll get added to the n equals 3 p subshell because we can fit 1 more electron in there. So that electron will add to the 3p subshell, and then it'll become 3p6 instead of 3p5. So when we form the chloride anion, there's a negative charge right here. We have 1s2, 2s2, 2p6, 3s2, 3p6. And that is also the same electron configuration as argon. So the calcium 2 plus ion, argon, and the chloride anion are all isoelectronic. They all have the same configuration. And let's look at another example. After chlorine, we can look at oxygen. Oxygen is a group 6A nonmetal. Neutral oxygen has a configuration of 1s2, 2s2, 2p4. We know that group 6A nonmetals like to gain 2 electrons. We learned at the beginning of the semester. And why would it like to gain 2 electrons? Its highest value of N is 2, and in its 2p subshell, a neutral oxygen atom has 4 electrons. And in order for that p subshell to be completely full, it can fit 2 more electrons in it, so it has 6. So oxygen will become the oxide anion, and it'll gain 2 electrons, so O2 minus. The configuration will be 1s2, 2s2, 2p6. So where did those electrons go for an anion? They went in the highest value of N, where there was space to fit those electrons. So we went from 2p4 to 2p6. We added 2 electrons to that 2p subshell that was not full, and now it is full. And the oxide ion has the same electron configuration as neon. So it's also isoelectronic with the sodium ion, neon, and O2 minus. Whether we're forming a cation or whether we're forming an anion, notice that when they lose electrons or when they gain electrons, they're trying to obtain noble gas configuration. And this is why noble gases are particularly stable. They have a completely full subshell. So they have a completely full p subshell in the case of noble gases. And so that grants them that extra stability, and they don't want to react because their p subshell already has the maximum number of electrons in it. And so metals will lose electrons to obtain noble gas configuration and have a completely full p subshell. And anions are going to gain electrons, so they gain as many as they need to finish filling up that p subshell. So we previously looked at forming cations and anions when we have representative elements or our main group elements. When we're looking at forming cations from our transition metals or our D block elements, we have to consider our order of filling and then how that's going to change when we're taking away an electron. So when we form a cation from a transition metal, first we lose 1 or more of their s electrons. After their s electrons are removed, we can possibly remove more from their d electrons. If you recall, transition metals don't just form one charge in most cases, they form multiple charges. And so looking at their electron configurations can help predict what charges they would form. When we build up the electronic structure, we're adding 1 electron at a time to the lowest energy valence shell. But every time we move from one element to the next, we're also adding a positive charge to the nucleus as well. When we remove an electron from the outer shell, or the highest value of N, it's not the exact reversal of that process of following the off-ball principle of building up, because when we remove electrons, we are not changing the number of protons in a nucleus in each case. We have the same number of protons, but now we're trying to yank an electron with a negative charge away. So what ends up happening is those s electrons get removed first, followed by the d electrons. So for iron, for example, the shorthand configuration is argon brackets brackets 4s2 3d6. When we form an iron 2+ ion, the electrons that get taken away first are these two 4s electrons. Those are going to be from the highest value of n, or n equal to 4. Those are going to be what we remove when we first form the iron 2+ ion. And then, if you recall, iron also forms a 3+ ion. Well, if it's a 3+ charge, it must have lost 3 electrons. So if we look at neutral iron, we know the first 2 electrons get taken away from the 4s. Where will that third electron come from? Well, that third electron is going to have to come from the 3d6. So 1 electron can get removed from the 3d subshell. That would mean for iron 3+, the configuration would be argon brackets brackets 3d5. Whereas for iron 2+, the configuration was argon brackets brackets 3d6. So even though we filled the d subshell last, when electrons get taken away, they get taken away from the highest value of n first. So 4 is higher than 3, therefore the 4s electrons get removed before any 3d electrons do. And this kind of helps explain why iron forms a +2 charge and a +3 charge as well. If we remove 2s electrons from iron, now we have electrons only occupying 3d. So it's like we took the 4s out of the picture. That's kind of a stable thing for transition metals, is to lose those s electrons. And then a 3+ charge forms because now we have 3d5, and we saw before that the 3d orbitals being all half filled is particularly stable. So often how many electrons are left in the d subshell will dictate what possible charges the transition metals can form in the first place. You might have noticed that if you look at the charges that a lot of our transition metals forms, that many of them form a +2 charge or a +2 oxidation state. And that's because they can lose electrons from that previous value of ns that filled before the d subshell that the transition metal electrons are in. And the ions that are higher than 2+ for the transition metals, those must all be the result of losing some of their d electrons. We can't easily predict what ions will form, but if we know that having completely filled or half-filled d subshells are extra stable, however many electrons it takes to get to that point, that'll be the ion that it'll form. So, for example, manganese 2+ forms, it ends up having argon brackets brackets 3d5. We saw iron 3+ that has the same configuration, argon brackets brackets 3d5. That 3d5 represents a completely half-filled d subshell. Zinc 2+ forms because it just loses its 4s electrons, and what it's left with then is argon brackets brackets 3d10, and having a completely filled d subshell is particularly stable. So the transition metals that will form when they become an ion is going to be dependent upon how stable the electrons that they're left with are. Practice predicting the ground state electron configuration for the following ions. Whenever you're writing the configuration for an ion, I suggest writing the neutral electron configuration first. So before we write the configuration for titanium 2+ and for titanium 4+, let's just write the configuration for neutral titanium. We can use the shorthand notation to make this easier. So the preceding noble gas for titanium, which is Z number 22, is going to be argon, brackets, brackets. And then after argon, which is in the 3rd period, we'd be in the 4th period. And so we would have 4s2. And then moving after calcium, we would have 3d1 and then 3d2 for where titanium is. So when titanium becomes an ion and it forms a +2 charge, what electrons are going to get removed first? Those are going to be from the highest value of n, or in this case 4. So these two 4s electrons will get removed first. Our electron configuration for titanium 2+ will be argon brackets brackets 3d2. And titanium also forms a +4 charge, and that makes sense why it would form a +4 charge as well, because there's 2 electrons hanging out in that 3d subshell, and those can be removed for it to attain noble gas configuration. So next, 2 electrons that will get lost will come from the 3d subshell. Now 3 would be the highest value of N that's left. So titanium 4 plus will be argon brackets brackets, and that's it. It doesn't have any other valence electrons. It has noble gas configuration, so it's stable. And we have, for our last example, the bromide anion. So our configuration for neutral bromine, atomic number 35. So Z is equal to 35. We're going to have our previous noble gas is argon as well. And after that, we're going to have 4s2, 3d10, and then 4p5. So bromine is a halogen, and our halogens gain 1 electron. When we add electrons, we're going to add electrons to the highest value of N in the orbital that can accept more electrons. So that's going to be our 4p. Right now we only have 5 electrons. We're going to put 1 more in there. So our configuration for bromide will be argon brackets brackets, 4s2, 3d10, 4p6. So we added 1 more electron to that 4p subshell. Let's try a few more. Predict the ground state electron configuration for the following ions. We have strontium 2 plus. So for neutral strontium, our atomic number, or Z, is equal to 38. So we would have 38 electrons to place. And if we write out our configuration, our preceding noble gas would be, before strontium would be krypton. So we would have brackets, krypton. And then after that, we're going to have 5s2. So we are in the 5th period, and we have 2 electrons that are filling that 5s subshell. And those are going to be the electrons that are living in the highest value of N. So the highest value of N in this case is 5. Those 2 electrons are going to be lost when strontium becomes a +2 ion. So our configuration for strontium 2 plus, we can write this in our shorthand notation of just saying it's the same as krypton brackets brackets. So those 2, krypton and strontium 2 plus, are isoelectronic. They have the same configuration. If we look at Y3 plus, our atomic number is Z equals 39. And for just neutral, we're going to have our preceding noble gas be krypton. So krypton brackets brackets. And then we're going to have 5s2. And then we're going to have 4d1. So remember, in the D block, the value of N is the period number -1, so that's why it's 4. And we're forming an ion with a 3 plus charge. So first, the electrons we are going to lose are going to be from the highest value of N, in this case 5. So we're going to take away those 2 5s electrons. And then we have 1 electron in the 4d. That would be the last one that gets removed. So we're taking away all 3 of those electrons. Our configuration will end up just being krypton brackets brackets. Lastly, we have the nitride ion N3-. If we write our configuration for nitrogen, our atomic number is 7, so Z equals 7. We're going to have our previous noble gas being helium, and we're going to have 2s2, 2p3, and in this case we're forming an anion, so we're not taking away electrons, we're adding electrons. Right now there are 3 electrons in the 2p subshell. We can have 6 electrons occupy a p subshell, so we're going to add 3 more to this highest value of N that can occupy more electrons. So our configuration is going to be, for nitride, which is N3-, helium brackets brackets, 2s2, 2p6. We added 3 electrons to that p subshell. And what is that the same as? That's the same as the noble gas neon. So nitride and neon are also isoelectronic. because they have the exact same electron configuration. So usually when an ion's forming, it's trying to attain noble gas configuration. That leads us to the following generalization we can say about when ions form to kind of sum up everything we've been talking about. Atoms from our representative elements, which those are our first two columns and our last six columns, those would be our S and our P block, will tend to gain or lose electrons to obtain the nearest noble gas electron configuration. So if they are a metal, they will lose those electrons to match the preceding noble gas. If they are a non-metal, they will gain the number of electrons they need to match the upcoming noble gas. Helium's kind of the exception to the rule. It has 2 electrons. All the other noble gases have 8 valence electrons in their highest shell, their highest N value. Whatever period they might be in would match that highest N value. We've been spending all this time talking about quantum numbers for electrons and orbitals and writing electron configurations for electrons and orbitals, but we haven't yet talked about the different shapes of the orbitals and their orientations in space. So a couple things we're going to be interested in knowing are the general shape of the orbital, what its size is, and its orientation in space relative to other orbitals. So we'll start with the lowest energy orbital, which is an s orbital. S orbitals are spherical in shape, and the size of an s orbital increases as its value of n increases. So as that principal quantum number goes up, the size of that sphere goes up. So a 2s orbital is larger than a 1s orbital, and a 3s orbital would be bigger than a 2s orbital. And as a result of that size increasing as n increases, that would mean that the probability of finding an electron is going to be farther and farther away from the nucleus. It'll be a function of distance from the nucleus. And since the 3s orbital is much bigger in size than a 1s orbital, the chances of finding an electron close to the nucleus are going to be less for a 3s orbital. Since a 1s orbital is spherical in shape, that means that if we go out a given distance from the nucleus in any direction, the probability of finding an electron is going to be the same, whether we go in the x, y, or z direction, since it's spherical. That means that all points of equal probability lie on the surface of a sphere. What's interesting is that for larger values of n, there are certain points where the electron density drops to 0. So in 2s, there is a node contained in that sphere where there's a 0 chance of finding an electron. If you recall, when we were looking at wave functions, and since these orbitals are actually wave functions, a node is a region where the wave function crosses 0. And so this would represent that 0 point, or our node, for a 2s orbital. And in a 3s orbital, there's actually 2 locations that are nodes. And so if we were to look at the wave function, there is 1 node and 2 nodes, 2 places where the wave function comes to 0. And that means that in that region, there is a 0 probability of finding an electron. Another type of useful image is a dot density diagram. A dot density diagram is an illustration that shows the probability of finding an electron and how it varies in space. If we look at the dot density diagram for a 1s orbital, we can see that the probability of finding an electron gets farther and farther away as we move away from the nucleus. So as we get away from that nucleus, the chances of finding an electron far out there is less and less and less. It's more likely that the electron is going to be found close to the nucleus where there's many dots. The dots become sparse as we move out because the chances of finding an electron out there are small. So we can use these density dot diagrams to help us visualize where it's most likely that we're going to be finding an electron inside of these orbitals. Next, we'll look at the p orbitals. P orbitals are quite different from s orbitals. P orbitals are dumbbell in shape, or some people would call them bow tie shaped. And their size also increases as n increases. So just like we saw with s orbitals, p orbitals get larger as our value of n goes up. And there's 3 equal energy p orbitals within any p subshell. We denote them by calling them px, py, pz. They're rather different from s orbitals in that the electron density is equally distributed in 2 lobes on opposite sides of the nucleus. So here we have one lobe, and here we have the other lobe, where there's a region that's running right through the nucleus where there's no electron density, and that would be a node. Because of this node running right through the middle of a p orbital, electrons that live in p orbitals cannot reach the nucleus as well as electrons in s orbitals can. This is what causes p orbitals to have slightly higher energy than our s orbitals. The 3 equal energy p orbitals are going to be oriented 90 degrees to one another. So a px orbital will lie along the x-axis, a py orbital will lie along the y-axis, and a pz orbital will lie along the z-axis. All 3 of them are going to have nodes that run right through their center. And the last picture shows us what all 3 p orbitals would look like together on the x, y, and z coordinate system. We can also see, looking at the density dot diagram, that there's that node lying right through the middle of a p orbital, and the dots get less and less as we reach the outer region of our orbital or of our wave function. So it's more likely to find electrons in our p orbital where the dots are heavy for our dot diagram. The last type of orbital that we're going to look at are d orbitals. D orbitals are a bit more complex than p orbitals. D orbitals are clover-shaped for 4 of them, so these would represent our first 4 clover-shaped ones, and then one that's sometimes called a dumbbell with a donut. Since they are so much more complex, it's hard to try to show all 5 d orbitals on one coordinate system. The first 4 d orbitals that have the same shape consist of 4 lobes of electron density. So we have 1 lobe, 2 lobe, 3 lobes, 4 lobes. It's almost like 2 p orbitals together. The first 4 d orbitals only differ in their orientation around the nucleus. So we can think about them as lying in a plane. This first one is often referred to as dxy because it lies in the xy plane. This one would be dxz, lying in the xz plane. dyz lies in the yz plane. And dx squared minus y squared lies in the xy plane, but its lobes are oriented directly along the x and y axis. The last one is referred to as a dumbbell with a donut, and the dumbbell lies directly along the z-plane, whereas the donut region lies in the xy plane. We will see that d orbitals are important in the formation of chemical bonds in certain molecules, and that their shapes and orientations are often important in understanding the properties of transition metals. They give many transition metals their special properties that we may have observed throughout this course.